Okay, in this video on NMR, we're going to put it all together for the proton NMR and see if we can interpret a complex table like this, with lots of data inside it, and come up with a structure at the end. Okay. Your best friend to help you during this process is the A-level data sheet or data booklet, and again we're going to be concentrating on this table here. So you've been told that compound X has the molecular formula C6H12O2. You've been given a variety of chemical shift data and the integration value for the number of hydrogens at a point, that signal, and also its splitting pattern. Okay, so how are you going to go about answering this? Well, the thing is, you've got to be logical, systematic, and show the examiner how you've got that assignment. So, for me, and this is the way I would approach it, is first of all, deduce what the integration value is for each signal. So, how many equivalent hydrogens have we got? Look at the chemical shift. Referencing to the data sheet, and finally look at the splitting pattern, and then write down what you think would be next to the hydrogens giving rise to the signal. Okay. Right, so the first thing is this, the integration values. We've been given a ratio, 0.6, 0.6, 0.6, 0.9, 0.9. We need to divide through by a number to give us a common factor. If we divide through each of these values here by 0.3, that gives us 0.6 divided by 0.3 gives us 2, 2, 2, 3, 3. Have we got the correct ratio? Well, the correct number of hydrogens. We've got 3, that's 6, 8, 10, 12. The molecular formula of our compound has 12 hydrogens, so we can be confident that we have got the right number of hydrogens here. Okay, so that's step number one. So we know in our molecule we've got 3 CH2s and 2 CH3s. Okay, so the next thing we're looking at is the chemical shift information. Okay, and we're going to use this in conjunction with the integration values that we've just calculated. Okay, and we're going to look at each chemical shift value in sequence, so just be logical about it and just go through them stepwise. So the first one is 3.7, so it's a CH2 because we know it's 2 hydrogens. We'll assume they're on the same carbon and that carbon's bonded to an oxygen, so it could either be an alcohol oxygen, an ether oxygen, or an ester oxygen. We're not quite sure at this point. 3.5. Now 3.5 is too low for it to be an ester. So we know that it's a CH2 bonded to an oxygen, and so we can say that it's going to be bonded to either an alcohol or an ether. Value at 2.6. Our data sheet tells us that those hydrogens are going to be bonded to a carbon which has got a C double bond on. Now again, we don't know whether it's an aldehyde, a ketone, or an ester. Because we don't know, we'll just leave it as those possibilities. 2.2, again, we've got our data sheet tells us that we've got hydrogens on a carbon next door to a C double bond on, which could be next to an aldehyde, a ketone, or an ester. Now, it's a CH3, so that means that carbon can only have one bond, so it must be to this part here. So, to be honest, we can rule out an aldehyde but again we'll just keep it there just for the moment. Finally, we've got at 1.1 ppm we have got a CH3 from our integration, and we know that it's bonded to an alkyl group, okay, because of the relative positioning of it. Okay, so that's the chemical shift data. Next, we're going to look at the splitting patterns. This is the most complicated bit to think about. Again, we're going to go through it sequentially. We're not going to try and join the molecule up, we're just going to try and report the different fragments. So, we've said already, it's a CH2 that is with carbons bonded to an oxygen. We said that oxygen could be alcohol, ether and ester. But we're concentrating on the splitting pattern here. It's a triplet. So using the n+1 rule, we know that these hydrogens on this carbon are next door to, or adjacent to, another CH2 group. The peak at signal at 3.5, again CH2 bonded to an oxygen. We now know, because it's a quartet, using the n+1 rule, that this CH2 group is next door to a methyl group. At 2.6, again we've got a triplet here, and we said that it was a CH2 bonded to a C double bond O. So we now know that on the other side of this carbon we have got another CH2 because of it being a triplet. Next, at 2.2, we have got a CH3 group which is bonded to a C double bond O. Now, because this carbon's already got 4 bonds to it, it has to be at the end of the chain, and it makes sense. It's a singlet. The adjacent carbon has no hydrogens on it. There's no hydrogens here, and you can't have a bond here. Finally, the signal at 1.1 ppm, it's a triplet. So we said already it was a CH3 attached to an alkyl group, part of an alkyl chain. Because it's a triplet, we can say that there's 2 hydrogens on the adjacent carbon because of the n+1 rule. And so now we've got some of our fragments. So the pieces are, we've got at 3.7 we've got this CH2 here bonded to an oxygen and also bonded to a CH2. The signal at 3.5, it's a CH2 bonded to an oxygen, but it's bonded to a CH3. So we now know that these 2 fragments, these 2 CH2 groups are in different environments. The 2.6 signal, we said it was a CH2 next to a carbon-oxygen double bond, but because it was a triplet, it's also next to another CH2. At 2.2, we've got a CH3 next to a C double bond O. And at 1.1 we've got a CH2 and a CH3, so it's part of an alkyl group chain, so it's the signal's due to the CH3 group. Okay, so how are we going to put it all together? Okay, so here are the fragments again. So what you've got to do is to look at which bits are in common. So you've got to say, well, I've got 2 CH2s here next to each other. Got 2 CH2s here next to each other. I've got a CH3 and a CH2, CH2 and a CH3, and a CH3 next to a C double bond O. Oh, that's got a C double bond O. So, how are we going to stitch it together? So, first of all, using this signal here, we've got a CH2 and a CH2 next to a C double bond O, and we've got a CH2 and a CH2 next to an oxygen. So these two CH2s are the same, and so one of these is bonded to the carbon of a carbonyl, the other carbon is bonded to an oxygen. Okay, I know it's a poor representation, but I just don't have the drawing package here. Okay, the next one, we've got a CH3 next to a CH2, which is joined to an oxygen. We know from 1.1 we've got a CH2 joined to a CH3. So that tells us that these two fragments are the same. So we've got a CH3, a CH2 onto an oxygen. We've got a CH3 bonded to a C double bond O, and well, that's the only thing it can be. So now we've got to look at these fragments. Can we stitch them together? Okay, and hopefully you can work out that you can perhaps on this carbonyl here is this carbonyl here, and this oxygen here is this oxygen here. Okay, if you want to try and draw down the structure, pause the video, do it now, because I'm now going to reveal the final answer. Okay, so here's the final answer. So we've got our methyl group here. It's a singlet. It comes in at about 2.2 ppm. Carbon-oxygen double bond, and then we had a CH2, which was a triplet, and that came in at 2.6 ppm. This CH2 here was a triplet, and it was at 3.5 ppm. And then we have 3.7 ppm, sorry. This CH2 here was at 3.5 ppm, and then this CH3 here was the signal at 1.1 ppm, which was a quartet. Okay. The big thing is, you will not, in your exam, you will not get more than two carbons containing hydrogens next to each other. So for example, you won't be expected to interpret a chain where you've got, say, CH3, CO, CH2, CH2, CH2O, because that middle carbon, so the middle carbon's hydrogens have a very complicated signal. Okay, I hope this helps for your interpretation. Just a couple of final points. We know it was never an alcohol because there was no singlet peak with one hydrogen in our data, and also we knew that it wasn't an aldehyde because there was no signal up around 9 to 10 ppm. Okay, thank you for watching. Best of luck in your exam.